My name is Luca, and I'd like to talk about MiniSearch, which is an open source library that I created a couple of years ago now. MiniSearch is a full text search engine which runs entirely in the browser. So again, this is not going to be a talk about Ruby, but hopefully still interesting for you. MiniSearch, I started working on MiniSearch initially to solve a problem that I had at work with my company. So my company, one of the most popular products that we have is an ordering application that shop owners use in order to order supplies from wholesalers. Now back then we wanted to offer a search functionality, and so that users could find products that they're looking for. Now this search functionality would have to search between inventories of wholesalers, which typically have something around a few thousands to a few tens of thousands of products. So we obviously wanted the search to be somehow robust to misspellings, or I don't know, not using the right diacritics, and to be convenient and fast as users expect search to be. Normally, one would use a search server to solve this kind of problem, something like Elasticsearch or Solr, and it definitely would have been a good solution in this case too. But the thing is, our application is prominently used on mobile devices and oftentimes on spotty network connections. So, in these situations, when you have to contact a search server, it's kind of hard to make it feel snappy. Search might lag because of connection problems and whatnot. So, I just started thinking, could this be done on the client side? I mean, sure, we won't be able to do that on the client side if we're talking about millions of documents, but tens of thousands of documents. Is it too much? Is it feasible? And this is the kind of challenge that I really like. And back then, I had just co-founded my company, and I was stressed because of lots of stuff to do, and I really found this kind of challenge quite motivating. The reason why it's motivating for me is because I actually really like algorithms and data structures. It's one of my favorite parts of software engineering. And the reason why I'm excited about it is because, to me, algorithms are appeal to this inner sense of engineering, engineering is quintessentially, to me, about solving problems. And algorithms are oftentimes like simple machines. They're relatively simple solutions to complex problems. So my favorite algorithms are not too much the kind of black box, complex machine learning, big data kind of algorithms, which for sure are interesting. But for me, my favorites are the simple ones, the ones that really make you go like, aha, wow, like when you finally understand how it's working, and it almost feels magic to me. Now, I don't want to imply to this that you have to be excited about algorithms and data structure too. And if you're not passionate about it, you're, I don't know, not a professional software developer. As a matter of fact, passion is not even required in our profession. If you're passionate, well, great for you. But and also, you don't have to be passionate about the same things that interest me. But yeah, that said, this is something that really excites me. I have to say that there are some pretty bad use cases for algorithms too. And I think the most prominent one is to use algorithms as whiteboard interview questions, right? I mean, possibly a few of us have been through this kind of experience of, being asked to, say, implement quick sort while the interviewer is looking over our shoulders. So, well, please don't do that. It's not only stressful for the person interviewed, but it's also really not useful for the interviewer, because it doesn't really tell us anything interesting about the candidate. That said, okay, well, when we have a problem at hand, I think one of the best ways to start is to formalize the problem, formalize our goal, and somehow the constraints. So in my case, again, I wanted to implement full text search functionalities. So I wanted this full text search engine to provide at least exact match, which is, okay, give me all the documents that exactly match a specific term. Prefix match, which means I'm starting to type something and I already want to get results that contain terms that have my search as a prefix. Like if I'm searching for uni, I want to find unicorn, university, universe, and so on. And fuzzy match, which is if I misspell what I'm searching, the system should be forgiving, like should still give me results unless I misspell it completely. Right. I also wanted to be able to search on multiple fields because our products have a title, have a description, have possibly barcodes, tags, and so on. And the user should be able to search in all of them. I wanted to have other common features in full text search, like boosting, which means, for example, I might want that if a search term is found in the title, that's more important than if it's found in the description. And the results should be returned in order of relevance. So more relevant results should be ordered first. The constraints were that, okay, if this search engine has to run on the client, the whole index must fit in the browser memory. And yet it still has to be performant enough for the user to feel immediate, right? There should be no noticeable lag. And again, like this calls for some specific trade-offs here, because the thing is, search servers like Elasticsearch or Solr or even the Postgres full text functionalities, they normally rely on having a lot of space at their disposal. When we run an Elasticsearch server, we normally run it on a machine with large amounts of memory. And even when memory is over, like it can always rely on the disk space, on gigabytes of disk space for storing the index. On the other hand, they should minimize computation because they need to be very fast with possibly many users using the search server at the same time. Now, for me, it was a very different trade-off because MiniSearch doesn't have a lot of space. It only runs in the browser memory, so it doesn't have access to gigabytes of space. Like tens of megabytes is already at the higher limit. On the other hand, I can afford a little bit more space when it comes to computation. Why? Because when you use a web application, usually you are the only user of this, like on the client side, like you're the only user of your own web browser, right? So yeah, for this reason, when search servers usually go all the way in the trade-off on the side of using a lot of space and minimizing computation. So for example, they use specific special purpose indexes for different kind of search strategies. They rather use a lot of space and make things simpler. In the case of MiniSearch, I couldn't do that. So I had to find an index data structure that could fulfill all the different goals that I had with one single general purpose index. And luckily, there is something like that. There is one, like the data structure that I ended up using is something which is called the Radix tree. It's actually quite simple in its nature. So it's a tree, so it's a tree kind of structure, which very much looks like prefix trees. It is just slightly compressed. So the way it works is, imagine that we have to store 4 words: Unicode, unicorn, university, and universe. Now we can rely on the fact that they all have the same prefix, which is uni. They all start with uni. So this will be the root of our tree. And then the 3 forks, there is unico, which has the words unicorn and unicode, right? Or universe, which has university and universe, and so on. So the tree goes on that way, as you can see here in the slide on the right side. And what are the properties of the Radix tree? Well, the Radix tree enables us to look up for terms contained into the data structure quite efficiently, because looking up a term takes at most a number of steps, which is the number of characters that compose the word. And normally when we search for something, we want to search for a search query which is 1,000,000 characters long, right? So normally the length of the word is a small number. It is also efficient to update. And it enables efficient prefix search, because if I want every term that, or every word that starts with universe, for example, well, I just walk down the tree, traverse the tree until looking for this prefix, and all the subtree contains exactly all the terms that have that specific prefix. And very interestingly, for my use case, the Radix tree is compact. Why? Because if you think about it, in this example that I have here, where we have 4 words, the Radix tree will contain less characters than the sum of all the words, because all the common prefixes are shared. So you can end up having a search index, which is actually smaller in size than the sum of all the words that are contained in the index, which is particularly important in our use case. And it is actually possible to implement fuzzy search on the prefix tree, on the Radix tree, in a way which is relatively efficient. It's not as fast as you can do with special purpose indexes used by typical search solutions like trigram indexes, but it is fast enough, especially in a browser environment where you only serve one single user. And yeah, I guess that you might want to see how MiniSearch actually works in code. So, in MiniSearch, you start with a collection of documents. I hope that the text is big enough for you to read. But again, you start from a collection of documents. Each document has to have a unique ID. In this case, I have 4 documents which represent 4 books. Each of them have a title and some text. And you have to instantiate MiniSearch. MiniSearch is a JavaScript library, so this is JavaScript code running in the browser. So you call the constructor of the MiniSearch class, telling it which fields you want to index, so which fields you want to search among. In this case, title and text. There are other options which I'm not going to go into because of time constraints. But yeah, after that, you can index your documents. So it's the last line in the screen, MiniSearch add all, which will add all the documents to the index. This step is normally really fast. So for tens of thousands of documents, it typically takes a fraction of a second. And yeah, then at this point, we can finally search. The first example here is the most basic search, which is the exact search. So we're searching for all the documents that contain Zen, art, motorcycle. And we will receive an array of results, which is sorted by relevance, so more relevant results first, and scored. So the score will tell us how relevant result is. But I can also search within specific fields. In the second example, we say, yeah, I want to search for documents that contain the word Zen, but only in the title. I don't care about, for example, the text or other fields. Or alternatively, I could boost some fields. In the third example, we say, well, still search on every field, but if the match is found in the title, make it count twice as if it was found, for example, in the text. I can perform prefix search. That's the first example in which I'm searching for moto, but I will get everything that starts from moto, like, for example, documents containing the word motorcycle. And or fuzzy search, in which I allow my search to contain some misspelling. I can give it a fuzziness argument in which I say how many mistakes I can tolerate, basically. And MiniSearch has a bonus feature, which is the auto-suggestion. So it is able to auto-complete your searches, like when you search on a search engine like DuckDuckGo or Google, that as you search, it provides you with suggestions and completes your search. MiniSearch is able to do that, and you don't need to do anything else than just index your documents. It's a bonus feature that comes with MiniSearch. Yeah, so maybe I have time to show you a very short demo. It's Actually, tell me, do you still see my screen and my browser? Okay, great. So the application that you're seeing here is
Sorry, we don't. We just see that.
Yeah, okay, exactly. Let me see if I can share the. Give me just a second. You share, and I'm gonna share my browser. Yes, now you should see my browser, right? Okay, so yeah, this is a sample application in which I'm indexing 5,000 top songs that went into the Billboard Top 100 between 1965 and 2015. So we can search for things like, let's say Backstreet Boys or whatnot. And as you can see, the results change as I type. You don't see any noticeable delay. So it's interesting to say that the indexing of these 5,000 documents happens every time upon page load. So there's no caching here. And yet, as you can see, it's basically unnoticeable. So it takes more time to load the page. You don't see any noticeable indexing time. Well, you can also see how you can get the suggestions for the search. Like I'm searching for Rolling Stone, and it gets me, okay, Rolling Stones, for example. And yeah, we have a few advanced options here in the demo. I can say, as I said, well, I only want to search in the artist field, or maybe only in the title. So I find like a Rolling Stone from Bob Dylan. I want to search, I can search, I can apply fuzzy search. So for example, if I turn off fuzzy search, I won't get like a Rolling Stone anymore because, yeah, for example, in this case, I don't get any result anymore because it doesn't match exactly Rolling Stones, right? And yeah, I can filter by year. For example, I can say, okay, give me all the songs from the artist Madonna until the year 1999, right? Yeah, and this happens completely on the client. There's no interaction with the search server. So yeah, I'll now go back 1 second to the slides. We are at the end of my talk. The last thing that I want to say is that this might feel a little bit like reinventing the wheel. There are very good search servers out there. And also there are even other libraries that similarly to MiniSearch perform full text search in the client. One interesting one is called Lunar. It's quite popular, and I contributed a couple of bug fixes to it, and the author is really nice, so I definitely can recommend it. But yeah, I think that reinventing the wheel is actually a lot of fun. At the early days of the Ruby on Rails community, there was this mantra of not reinventing the wheel. But I think we sometimes misunderstand it. In my opinion, the actual meaning is you don't have to invent the wheel. So if you're working on a project, you don't have to rewrite from scratch everything. You can pick and choose among a lot of different libraries and frameworks and whatnot. But it doesn't mean that you should not reinvent the wheel. So if you, like me, sometimes find pleasure in writing libraries and you want to spend your effort into something that has already been done, I mean, I don't think that should be a reason not to do that. At the end of the day, the world evolves by reinventing the wheels. Entire art fields wouldn't even exist if people would not be reinventing and remixing. Yeah, so that's basically the end of what I wanted to say. I'm Luca Ongaro. You can find me on different platforms, GitHub, Twitter, on the web, where I also occasionally write some blog posts, very rarely actually, but there is a blog post about MiniSearch on my website in case you're interested in more details.